Good morning, afternoon, and evening, everybody. Welcome to the inaugural NfoLD seminar series. This is a seminar series that we hope to do every other month for the foreseeable future. If you're interested in being a speaker for the seminar series, please let us know at contact@nfold@gmail.com. We're looking for speakers for April, June, and August for now. Again, it's a wonderful opportunity to share your research, and please encourage your students to share their research as well. It's supposed to be fairly informal, 20 minutes, 30 minutes to give a presentation on the exciting things that you're working on. And so for this month, I'm very delighted and thankful for Dr. Danny Glavin of the Goddard Space Flight Center to be our inaugural seminar speaker. And please, if you are not speaking, please make sure your microphone is muted. It is distracting otherwise. Dr. Glavin received his Ph.D. in Earth Sciences from the Scripps Institution of Oceanography, and he researches the building blocks of life in extraterrestrial materials, including meteorites, asteroids, comets, and other interdisciplinary interplanetary particles. The title of his talk is The Search for Chiral Asymmetry as a Potential Biosignature in Our Solar System. Thank you again, Danny, and the floor is yours.
Thank you, Sanjoy. Can everybody hear me okay? I guess everybody won't speak at once. Okay, sounds good. So anyway, it's a real pleasure to be here today to be able to talk about chirality in general and how we can use it as a potential biosignature. What I'm going to talk about today was recently published online, I guess a few months ago now, in Chemical Reviews. The address is at the bottom of this first slide. So I encourage you to all take a look at that because I'm just not going to have enough time to go into all the details that are in the review paper. The paper should be out on June 10th, 2020 in a special issue online. And I do want to recognize my co-authors, Aaron Burton, Jamie Elsla, Jose Aponte, and Jason Dworkin, who really helped me think about this kind of new criteria, new strategy for how we can determine the origin of any chiral asymmetry in our solar system. So, is it moving ahead? How do I go forward here? Okay, there we go. So just quickly, motivation for this research. Any search for evidence of life in our solar system will certainly include some of the characteristic features of life as we know it. Homochirality is one of those, and that is the strong preference for L amino acids in proteins and enzymes and D sugars in the nucleic acids. There's a recent publication in Astrobiology, 2018, that brought forward NASA's ladder of life detection with a summary of several biosignatures, not just chirality. One thing that caught my eye was the criteria that greater than 20% enantiomeric excesses of amino acids would be a likely biosignature, provided that you could rule out the usual instrument contamination sources and that kind of thing. And this struck a chord because we know from our analysis of primitive meteorites that L amino acid excesses as high as now 60%, and D sugar acid excesses, which is not my work, that's a lot of the work from Cooper and Rios, have found up to enantiopure, 100% EEs that were produced on the parent asteroid by non-biological processes. So this definitely complicates the use of chirality as a definitive biosignature. And so here what I'm going to talk about is a set of measurement criteria to establish the origin, which of course includes chiral asymmetry itself, having that, and then the isotopic composition as well as a distribution that can really be used to hone in on the source. And at the end of the talk, I'll give a few kind of concrete examples of how we can use this framework to establish that. So just some quick background. I'm sure many of you are already familiar with this, but chirality is handedness, and that's why you often hear the terms left-handed amino acids and right-handed sugars and that kind of thing. It was originally discovered by Louis Pasteur in 1849, who was looking at the effect, the rotation of polarized light on crystals. in this case, tartaric acid crystals. And he noticed that, the dextro crystal would rotate light in one direction, and the levo rotary would rotate right in the other direction. And then when the two crystals were combined as equal mixtures, they wouldn't rotate polarized light, basically a canceling effect. There are a lot of other examples of chirality, chemical and physical, in our life. I think it's kind of interesting, and actually let me first just use the Tetris example here. You can see that spinning, but basically it's non-superimposable images. So chemically identical, but different in the orientation in space. And chirality can have a big impact. Some chemicals smell differently, like limonene, depending on the handedness. Other chemicals can be dangerous or less dangerous. Methamphetamine is an example. And so these chirality can definitely have a big impact on things. What we're going to focus on today is amino acid chirality, the bottom left there. So the origin of homochirality is a mystery. I mean, we know it's a fundamental property of life. You simply, proteins don't fold well, tertiary structures and that kind of thing, unless they're all of one-handedness, in this case, left-handed amino acids. The same can be said for ribose and deoxyribose. Provides the backbone of RNA and DNA, where you can't mix the two. You don't get the right helicity, the double helix structure. And I thought it was interesting to point out that Milton in the early 90s demonstrated that you could make an enzyme solely out of right-handed amino acids, D-amino acids, and it had the same functionality as the left-handed version of the same enzyme, but not with a mixture. And similar experiments have been carried out with DNA as well. They've made left-handed DNA out of left-handed sugars. Now, in contrast to life, all known non-biological syntheses, abiotic reactions, in the absence of a chiral force, produce racemic mixtures. And this is probably the most notable experiment was that by Miller and Urey in the early 50s, where they sparked a mixture of methane, ammonia, water, and CO2 and made amino acids that were always produced as a racemic mixture, so equal mixtures of left and right-handed form. So there's some key questions in Origin of Life surrounding the homochirality question. How did it emerge? When did it emerge? Why is life based on left-handed amino acids and right-handed sugars and not the other way around? Some have argued that the early Earth prebiotic soup would have been of equal mixtures of both hands. And so was it a 50-50 chance or not? And I guess to get to the punchline, it's starting to look like from our analysis of primitive meteorites and eventually return samples from small bodies that we hope to get in the future, that there was an early solar system bias towards left-handed amino acids and right-handed sugars. Okay, so just real quickly, this is the workup and analysis protocols that we use in our lab today. On the left, you see, I actually can't remember which meteorite that was, maybe Murchison. But we typically, crush up sugar cube sized fragments into a powder. That powder gets extracted in water, 100 degrees C for 24 hours. We're actually now working on other extraction protocols that use non-polar solvents as well. Those extracts then get acid hydrolyzed to free up any bound amino acids or convert acid labile amino acid precursors into amino acids. And then we take those mixtures through a series of purification steps, such as desalting to remove salts and other metal ions that can interfere with our derivatization reactions. And then we get the purified extract and we label it. And I'll talk a little bit more about that chemistry. And in our lab, we typically analyze these extracts with liquid chromatography, mass spectrometry to measure trace abundances of amino acids and also measure their chirality. So we get the D/L ratio. And then gas chromatography, isotope ratio mass spectrometry, where we can actually determine the isotopic, compound specific, amino acid specific isotope ratios in carbon, nitrogen, and hydrogen. This turns out to be a really important part of determining the origin of any enantiomeric excesses, and I'll talk about that more. Okay, so we know biochemistry is distinct from abiotic chemistry in a lot of different ways. Biology has 20 standard amino acids. There are a couple non-standard ones that are encoded in terrestrial proteins. So the 20 are listed there, all of the left-handed form, except for glycine, which is non-chiral. And then you contrast that with meteorites. So on the right is a picture of the Murchison meteorite. And to date, 96 amino acids have been named in this meteorite alone, including 12 of the protein amino acids, and those are highlighted in the blue color there as well. And hundreds of amino acids that are rare, non-protein amino acids and other rare amino acids have been detected in Murchison, but have yet to be identified. And I'll show a slide on that later, but you know, tons of complexity here. Life on the other side, again, as I pointed out, only the L-alpha amino acid is incorporated into proteins. There are other non-coded amino acids that occur in biology that aren't alpha, and I'll give a couple examples of those. In contrast to that, most of the amino acids in meteorites are racemic, with the exception of these few that I'll talk about that have large L excesses. And they exhibit basically near complete structural diversity. So you get all isomers, not just the alpha found in life, but beta, gamma, and delta. So again, a lot of complexity and diversity here. And then of course the sugars, which I'm not going to spend a whole lot of time on that topic. That would be a whole separate webinar in and of itself. And I'm not an expert in the sugar analyses, but maybe in the future, somebody would be willing to talk about that. But of course, D-ribose and D2 deoxyribose are the components of DNA and RNA. And interestingly enough, recently, Furukawa reported in PNAS that several of the bioessential sugars, including ribose, arabinose, and xylose, are also found in meteorites, which is pretty cool. And then Cooper and Rios have done a lot of work on the sugar acids and sugar alcohols in meteorites. They're there, abundant. And interestingly enough, some of the 5-carbon and 6-carbon sugar acids are enantiopure. So 100% of the right-handed form, which is just amazing. I think there's still a lot of work to do to figure out how you can get that type of enrichment. And I mentioned the amino acid complexity in Murchison, and here it is, kind of in all its glory. This is a liquid chromatography, time of flight mass spectrometry analysis of, again, the extract from meteorite. Carbon amino acids, glycine, which is achiral, all the way up to 10 carbon amino acids. Notice that trace at the top is magnified 40 times. So you're starting really to get towards the signal to noise level there. And you know, as you get heavier, it gets more difficult to separate out these peaks, which is why we haven't been able to identify a lot of the amino acids that are 7 carbon and higher. We've done a pretty good job in our lab identifying up to the C5 carbon amino acids. Those are shown here again, alpha, beta, gamma, and delta amino acids. There are actually 23 different amino acid enantiomers and isomers of the 5 carbon amino acids, and we've identified them all in Murchison. And I highlight the C5s because I want to talk about isovaline, which is a C5 amino acid. It's very unusual. And the reason it's interesting is because we get these relatively large left-handed isovaline excesses in Murchison. And this has been known for quite some time. Actually, Cronin and Pizzarello made these measurements back and reported them back in 1997, these L excesses. And I remember it was very controversial at the time, and GCMS measurements were used to make it, hadn't been independently confirmed. And it wasn't until 2009 where we developed an approach to measure this using liquid chromatography mass spectrometry. And again, we're able to confirm these results. Just really incredible. The origin of the asymmetry is not clear. I'll talk about maybe one hypothesis for how it may have formed. But what we can say is it's not from terrestrial contamination. This is an extremely rare non-protein amino acid. And the excess also appears to be correlated with the degree of hydrothermal activity on the meteorite parent bodies, which is interesting. And it's not just Murchison. These excesses have been observed in a variety of different carbonaceous meteorites. and that's shown here. So we've analyzed actually all 8 different groups of carbonaceous chondrites. And these are the ones where we actually detect isovaline. You don't see isovaline in the real thermally altered carbonaceous chondrites, the CVs and COs, but you see it in all the others. And yeah, it ranges from around 0 up to, I think the record now is 20.5% in one of the CH carbonaceous chondrites. And again, just pointing out that the least aqueously altered meteorites don't really have any measurable L isovalent excesses, at least within our air. They could be there, but they're smaller than our 2 to 3% measurement error. And most importantly, no right-handed isovalent excesses have been reported in any meteorite to date. And again, this is pointing at this sort of inherent early solar system bias towards L-amino acids. Okay, so it's not just non-protein amino acids that show this excess. We're also finding them now with protein amino acids. In this case, I'm showing some results from the Tagish Lake meteorite, which fell in Canada back in 2000. And this is a really exciting meteorite. You know, it fell in ice. Many pieces had been kept frozen, so pristine. And we saw these really large L-aspartic acid excesses, and which was unusual. And around 60% there, you can see the L peak bigger than the D peak. And what was equally interesting is we didn't see similar L excesses of alanine, which is another very common protein amino acid. It was nearly racemic in the Tagish Lake. So whatever amplification mechanism was working on this meteorite, it was favoring L-aspartic over alanine. And I'll talk about that later. Now, of course, you've got to take great caution when you're dealing with protein amino acids because they are common and they can be terrestrial contaminants, which again, could explain some of the L excess. And so you really need to do complete GSFC analyses to rule out interfering compounds, as well as compound-specific isotopic measurements. And we did that in this case. And we confirmed by carbon isotopic measurements that these amino acids were heavily enriched in the heavier isotope of carbon, carbon-13. And this is just something you simply don't find in biology. This is common for amino acids that formed in cold environments in space, but not in terrestrial biology. And I show the formula down here. It's basically in delta notation, but there's the equation. It's basically looking at the relative abundance of carbon-13 to carbon-12. And in general, there are exceptions, but in general, if you measure a delta 13C value above 0, then it's likely extraterrestrial. And I'll talk about that a little more. So you got to have these isotopic measurements to figure out whether your L excess is indeed non-terrestrial. So how do these amino acids form during parent? How do they form on the asteroid parent body? Well, we think it's during this aqueous alteration phase, which probably happened very early on in the solar system, first 10 million years or so, where you had these short-lived radioisotopes, aluminum-26 and iron-60, that could provide a heat source and melt the ice inside these chondritic parent bodies. Once you melt the ice with all the chemical precursors of amino acids, you can drive a lot of chemistry, and that's shown there on the left. And we think all of these reactions were taking place on some of these carbonaceous meteorite parent bodies. And it's not just aqueous reactions. Some of the high temperature carbonaceous chondrites that experience heat, but not so much water. We have evidence now for Haber-Bosch-Fischer-Tropsch type chemistry. These are gas phase reactions which produce achiral amino acids and straight chained compounds. And I'll talk more about that. So all of these reactions should result in achiral or racemic mixtures with near complete structural diversity. So the question is, what the heck is going on with these L-amino acid excesses? The chemistry just doesn't predict that they should be there. I'm going to talk about that now. So I think the leading hypothesis for what's going on here is that you had circularly polarized radiation exposure in the early solar system. So dust grains with amino acids in their precursors could have been exposed to this circularly polarized light, which could have either preferentially synthesized or destroyed one hand over the other. And it would depend on the polarization of the light itself that these grains were exposed to. And in fact, we see this polarized light in the Orion Nebula, for example, which is released from these massive O and B type stars. And up to 17% polarization can be found, which is pretty significant. So you can imagine early on in the solar system, the materials that eventually made up the material in our solar system were exposed to this polarized radiation. And lab experiments have shown that you can induce asymmetry on the order of a few percent, but not a whole lot more. So it doesn't explain the entire magnitude of the L excesses that we're seeing, but at least it's a credible way of breaking an initial symmetry and creating a small left-handed bias. Cornelia and Meinert published back in 2012. They've been doing a lot of work studying the anisotropy under different UV wavelengths of several different alpha amino acids. And they find that, and this is basically a measure of the effectiveness of polarized light to break the symmetry. And indeed, for isovalene shown, that they show that depending on the direction of the polarization, you can induce excesses of at least 2 to 3%. And it's not just true for isovalene, it's true for most of the alpha amino acids that they've studied. So that's pretty interesting. But again, we need another explanation for the large L excesses, you know, these 60%, 20 to 60% L excesses that we're seeing. And right now, the leading hypothesis for how this happened is basically amplification of those polarized light small excesses during aqueous alteration. So Wiedma and Klusman back in 2006 and 2008 showed through laboratory experiments that just crystallizing amino acids from solution can amplify them. So you have these conglomerate crystals shown on the left, which would include spartic, glutamic acid, threonine, and isovalene. And through multiple episodes of basically dissolution and precipitation forming these crystals, coupled with racemization, so you do need to convert the two, you can actually build up solid L crystals over right-handed forms through this process of conglomerate crystallization. So this is pretty interesting. It does require, again, that you start out with asymmetry, so you can't start out with equal mixtures of left and right-handed crystals and get this amplification. There has to be some initial asymmetry, but you don't need a whole lot. You know, even 0.5% asymmetry could result in amplification of much larger excesses. And again, we believe this happens inside the asteroid parent body during aqueous alteration. Now, in contrast to the conglomerate crystals, racemic crystals, which interestingly enough, alanine is one of those, which only forms crystals that are racemic mixes, would eventually be driven towards a more racemic mixture, even with a slight excess. And so again, this may be explaining why we do see these large L excesses with aspartic and glutamic and isovalene, but not in alanine. Again, I just summarized that in words, but right now this is our best explanation for how you get these large L excesses of some, but not all amino acids. Okay, so let's kind of apply our knowledge here to some hypothetical chiral distributions and their possible origins. So the right-handed amino acids are shown in blue, left-handed in orange, and we're looking at different relative abundances. So starting on the left, if we see left-handed much greater than right-handed, again, depending on the amino acid, that could either indicate abiotic chemistry, such as those amplification processes I just spoke about, or extant biology. I think probably the most unambiguous evidence for extant biology would be detecting the right-handed form in great excess over the left-handed form. The reason for this is simply because we could rule out terrestrial contamination entirely, since life is based on the left-handed form. And also, we have no evidence so far of any bias in the early solar system towards the right-handed form. So this could be, yeah, this would be a really exciting discovery. Probably the most challenging case would be in the middle there, where you have a racemic mixture that could either be produced by abiotic chemistry or could represent biotic chemistry, but that became extinct and had racemized over time to equal mixtures. That's a possibility as well. And then on the right, some less compelling cases, but interesting, where you have just slight excesses of one hand over the other. And again here, even detecting a small right-handed excess over left-handed, the left-handed form would be pretty exciting and could possibly indicate an extinct biotic chemical reaction. So again, how can we distinguish between abiotic and biotic sources in cases where the left-handed is greater than the right-handed? Which I would probably be the first to argue that may be the most likely case in our solar system, considering that the evidence is showing that we were biased towards the left-handed form from the very beginning. Well, isotopes will be key here. In terrestrial biology, there's a strong preference towards the lighter isotopes, carbon-12, nitrogen-14, and hydrogen, as opposed to deuterium. And if you measure these organics, in this case, amino acids and polyols, in both terrestrial samples and extraterrestrial samples, you can see that you can easily pull out the sources if you can do, for example, the D to H and the carbon-13 to carbon-12 measurement. You'll notice that even in extraterrestrial amino acids, there's some overlap, albeit very small, in the carbon isotope value, but when you measure the D to H ratio, they come apart. So a pretty conclusive way to determine the source would be to measure both D to H and carbon-13 to carbon-12. So this is pretty exciting. Obviously gives us hope that isotopes can provide some valuable information. Now again, this is based on terrestrial biochemistry, and you'd have to be careful going into an extraterrestrial environment that you understood the isotopic reservoirs and the fractionation processes and that kind of thing. So this is by no means conclusive, but important nonetheless. Okay, so here's again the Venn diagram that we put together that we use to establish the origin of any chiral excesses. And I'll go through some examples here. So let's take the Tagish Lake Murchison meteorite example. And I've spoken about both of these meteorites. They both have chiral asymmetry. Great, so we can check that box. In this case, pretty large. Aspartic acid has leftover right-handed excesses on the order of 60%. Problem here is that the distribution is it's too complex. And we can explain that distribution by abiotic chemical reactions. So we see near complete structural diversity, including a variety of rare non-protein amino acids. So doesn't pass the simple distribution check. And then finally, the amino acids are heavily enriched in carbon-13, so no evidence of biological fractionation processes here. So this is a clear case of abiotic chemistry, and we knew that, but just making sure that our criteria are working. It's designed. Okay, so here's another example, OSIRIS-REx meteorite. This is actually a really exciting meteorite. It fell recently in Costa Rica on April 23rd. And some of the original hunters, Mike Farmer and Robert Ward, noticed that samples that had been exposed to water gave off a very pungent odor, similar to the kinds of smells that they had experienced with Murchison meteorite. And indeed, it was classified as a carbonaceous chondrite, CM2 carbonaceous meteorite. Although it's notable, and you can just see from the picture on the left, that some pieces were clearly contaminated, not only by the landing site soil, but fingerprints, unfortunately. But nevertheless, this provides a good example of a meteorite that has evidence for both abiotic and biotic, in this case, terrestrial contamination. So we see the chiral asymmetry, in this case, L-glutamic acid, 60% L excess. But we also see a complex distribution in OSIRIS-REx. We see AIB and isovaline, and I don't show it here, but the C5 to C10 amino acids are present. It looks very similar to Murchison in that respect. So near complete structural diversity, not a simple distribution, so that fails that. And then here we actually see evidence of both carbon-13 enriched and depleted amino acids. So you see the right-handed glutamic acid, the D-glu, has a delta 13C value of plus 20 per mil, whereas the left-handed form is light, minus 10 per mil. And again, we think originally that these isotopic values were probably very similar and heavy, but terrestrial L-glutamic acid contamination with a light isotopic composition has lowered that value. So again, this provides an example of biotic and abiotic signatures in the same meteorite. Okay, so you got to provide the biotic only case, and we get that just by looking at the soil. Costa Rica has got a lot of bacteria in the soil, as evidence from this analysis. And you see it on the bottom left here. This is a liquid chromatograph time of flight mass spectrometry measurement. We see all the usual most abundant protein amino acid suspects here, heavily enriched in L over D. So we've got the chiral asymmetry. We do have the simple distribution here. We don't see much above 7 carbons like we see in the meteorites. It kind of cuts off at isoleucine here. And we do have a few amino acids that are non-alpha, so beta alanine and GABA, but they're at relatively low abundances. And also we think these are actually decarboxylation products from aspartic and glutamic, bacterially mediated. So again, not part of the protein structure, but nevertheless present at trace levels. And then finally, light isotopic composition. So all the amino acids show delta 13C values that are negative. So again, biology and no big surprise here. Okay, so this is an interesting case. And unfortunately, this result kind of went under the radar. There's so much emphasis on Alan Hill's 8401 over the years that I think some people forgot about RBT 04262, which was another Antarctic Martian meteorite, much younger than ALH 8401, which is about 4 billion years. This one's 225 million years. Ejected from Mars 3 million years ago and recovered in Antarctica in 2004 by ANSMET. And what makes this meteorite so exciting is it's the first meteorite that we've analyzed in our lab that didn't have a lot of evidence for terrestrial amino acid contamination from the ice. And in fact, we see a simple distribution of straight chain and omega amino acids. If you recall back, these are the ones that we think are formed by gas phase reactions, Haber-Bosch, Fischer-Tropsch type chemistry. And we see a similar distribution in some of the thermally altered carbonaceous chondrites as well. And again, if you look at the distribution in the bottom left, the ice just doesn't have a whole lot of these. So terrestrial contamination is just not a credible explanation here. Now we also have the isotopic composition, which was pretty interesting. We measured the delta 13C of beta alanine in RBT, and it was minus 26 per mil. And interestingly enough, this was similar to the carbon isotope ratios that Andrew Steele had been measuring from some of the macromolecular carbon in these thermally altered Mars meteorites. So again, we think it's kind of maybe an igneous high temperature origin of this material. So that's all really exciting. And you're thinking, yeah, we're onto something. But again, unfortunately, these amino acids are all achiral. So if we think chirality is fundamental to biochemistry, then this doesn't pass that test. So again, to us, this is pointing towards abiotic chemistry, not biological chemistry. Okay, so looking ahead to the future, this is actually a really exciting mission, ExoMars rover, which for the first time will land on Mars and drill down a couple of meters, which we think is actually really important because the surface of Mars is exposed to UV and ionizing radiation that can penetrate, down up to a meter or so and modify organic compounds. So if we want to get to the pristine material, drilling is really important. NASA Goddard built the mass spectrometer for the MoMA instrument, the PI's Will Brinkerhoff, and it has both GC and mass spec and laser desorption mass spec capability. And then the other notable thing about this instrument is it'll be the first amino acid chirality measurements made on Mars. Most of you know, but MSL is currently carrying out a search for organics and has found some interesting compounds. And we also have wet chemistry on SAM, but we don't have the ability to measure the chirality of any amino acids we detect. So this will be the first time. And again, you see a chromatogram that was done in a lab under MoMA-like conditions showing the separation potential for these compounds. So this is all really exciting. One important caveat here is that there is no compound-specific isotopic analysis capability here. So we can't measure the carbon 13 to 12 ratio or D to H or 15 to 14 ratio of the amino acids. So that's something that is actually potentially doable in the future, but will take some effort to make sure that technology is spaceflight ready. So in the meantime, we've got our hopes are pinned on Mars sample return campaign. Mars 2020 is the start of that, which is an MSL-like rover that will carry some remote spectroscopic instruments to try to identify the most promising samples. But the unique thing with this mission is it has the coring and caching capability. So it can actually collect cores and seal them for future Earth return. And I'm certainly one of those that tend to be biased towards lab measurements. I've seen the power and the capability that we have, and the technology just improves with time. And I think that ultimately this may be our best chance of at least unambiguous assignments of biosignatures on Mars. We'll see. Hopefully ExoMars proves me wrong. NASA's certainly on board with this strategy of getting samples back to Earth so we can subject them to some of the best instrumentation we have available. Okay, so I don't think I need to read through all these conclusions, but I think the bottom line is we know there are non-biological processes that can lead to large left-handed amino acid excesses, and we need to note that and be careful about that. Isotopic measurements are going to be very important for establishing the origin of any excesses that we detect. And looking for some exciting times ahead with ExoMars and eventually Mars sample return, so we can put this biosignature to the test, if you will. And I'd like to thank you all for your attention, and happy to take questions.
Question on the Costa Rican meteorite, and then another one after that if there's time. This is Dave DeMarais.
Hi, Dave.
Kai, can we go back to your slide that showing the data there and
Wait, the Martian meteorite or Costa Rican?
Costa Rican. Well, let's see. The one where you said there was a mixed origin.
Yep. Let me.
Okay.
Yeah.
It seems like you also have to have a green check by the distribution one, because there are biological amino acids in there from Earth, and it should be consistent with your isotopic observations. So just wonder how you would handle that, since you know that you have both abiotic or non-Earth as well as Earth-sourced compounds.
Yeah, so I guess when I talk about the simple distribution, I'm thinking more in terms of the the preference towards alpha hydrogen amino acids in terrestrial biochemistry and that kind of thing. Whereas in Aguas Arcas, we see the alpha dialkyls, beta, gamma, delta. I don't show them all here, but think back to actually, let me go back to the Murchison plot, which I think shows it better. Where are you? There. So this is kind of what Aguas Arcas looks like. So, tons of amino acid complexity and diversity. Yes, we have the L contamination, the protein amino acids on top of that, but they're both there. So I don't know if that answers your questions, but I was just trying to point out a case where we had a clearly contaminated meteorite that contained both evidence for terrestrial biological contamination and abiotic chemistry that happened before that meteorite landed and hit the Earth and was contaminated by bacteria and that kind of thing.
Yeah, anyway, it just seems like a way to enhance the method would be to, going back to that Costa Rican one. Since the isotopes do show you mixed origins, there has to be a consistency, I would think, with the molecular distribution. And how do you handle like 20%, 80%, 80%, 20%? I mean, it's the distribution thing needs to become more sophisticated to deal with what could be a very common situation.
Yeah, no, I think I accept that input. And if you have any thoughts, please email me and maybe we can think more about this. I will say that in this case where we had the 60% L-glutamic acid excess, we actually calculated just on mass balance what the isotopic value of that additional L-glutamic excess should be, and it was around -15 per mil to lower that value, assuming it was +20 originally, and that was the exact value of the L-glutamic acid in the Aguas Arcas soil. So I think in this case it was pretty clear that all of that L-glutamic excess could be attributed to terrestrial L-glutamic acid contamination from the soil.
No, that's a great approach. I got another question, but maybe I'll let somebody else go next.
Okay.
So Danny, I have a related question. Can you hear me?
Yes, I can, Paul.
So it seems like on Earth, the simplicity of the distribution might have to do with the fact that biology just totally dominates and the microbes eat everything that's available in terms of carbon. But if you're looking at, let's say sparse life on the surface of Mars, where there might be mixing from stuff falling in, or if you're looking at, a mantle water interaction on Europa and Enceladus, where the basic formation of that might be a carbonaceous chondrite, then it seems like the argument of the simple distribution might fall down a little bit, because everything's, the life might be mixed in with the abiotic stuff. What do you think about that?
Yeah, I mean, I think that's kind of what Dave was pointing at, right? Exactly that scenario. I tried to capture that here, but I think I failed. So, but I guess my point here is I think you can start to pull out biotic versus abiotic signatures, but you're right, Paul, this isn't going to be easy.
And so it might be something like, if you had an additional checkbox of non-amino acid type patterns or something like that, that might kind of add to the story.
Sure. Yeah, no, I mean, I think this review paper and this talk is really focused on the asymmetry, but yeah, you could think about other chiral compounds or just, other compounds in general. I mean, I know a lot of thought's been going into fatty acids and the even versus odd distribution. And so I think this is just as one of many biosignatures that we're going to be looking for. So this isn't the entire story. There's no question about that. There'll be more. But I guess the point I wanted to make is you really need to be thinking about all three of these things, not any one in isolation.
Yeah, great. Agree. Thanks.
Let me just make a little addendum comment to that. One of the new things coming out in the MEPAC goals document is going to be the importance of investigating the possibility of prebiotic chemistry on Mars as a complement to the biosignature approach. And you have this interesting situation where you're transitioning from abiotic to prebiotic to biotic, and what's the molecular distribution going to look like when you're in that gray zone?
Yeah.
It's anybody's guess, but again, these molecular distributions are probably going to be front and center in that.
Yeah. So one of the things, getting back to Mars now, one of the reasons the RBT result got me so excited, let's hear, is, these are all achiral amino acids, these long chains, and, we now have evidence that they're at least in one Martian meteorite. We argue this is subsurface material of igneous origin and that kind of thing. But at least it gives us one example of abiotic chemistry on Mars. So just, finding any amino acid that is chiral, that's an indigenous to a Mars sample, would be really exciting and potentially very different from the chemistry of these igneous rocks. So I'm hopeful. I think, we're starting to get some context here through the meteorite analyses, and we're going to learn a whole heck of a lot more with ExoMars and eventually Mars sample return as well. But it's not going to be easy. And you're right, it's probably going to be a mixture of things, and potentially we'll be dealing with that gray area as well.
Thank you, Danny. Any other questions for him?
Oh, I got another one, but I'm waiting for anybody else who's not spoken yet to jump in.
Yeah, well, kind of one of the messages, I think, any kind of biosignature that we propose needs to go through this kind of scrutiny. Some of the questions that have been raised are good ones, but, with actual lab results as well, looking at examples of abiotic chemistry compared to biochemistry. we really need to think hard about these.
If nobody else has a question, I'd like to go to your isotope one where you showed the deuterium enrichment and C13 enrichment. You had plots there.
Yeah, hang on a sec.
You might figured I was going to ask you an isotope question.
And I'm not an isotope expert, but that's okay.
Okay, so this is a great criteria for detecting contamination, earth contamination. And, if you get these positive numbers, you know that, you're dealing with an extraterrestrial source probably. But of course, we're in the business of finding evidence of extraterrestrial organisms, and we have no idea what the hydrogen and carbon pools are that they're pulling from. So this to me is a big challenge of using isotopes on Mars or elsewhere. And you mentioned this, what are the major geochemical pools, and therefore what's the substrate that life is working on? So I just wanted to say that in C13 and deuterium enriched compounds, might be evidence of extraterrestrial activity, but it's not clear how we would use them to look for extraterrestrial life working from different element pools. So I think that's just a big caveat about isotopes, beyond just proving that it's not terrestrial contamination.
Yeah, no, I agree with you 100%, Dave. I think one of the things I did want to point out with the slide is that one isotope measurement is probably not enough. You need multiple to start pulling out these sources as well.
And at the molecular level, as you mentioned.
Yep.
Any other questions for Danny? So there are 25 of you online, which is amazing. I'm hoping somebody can volunteer to give the April talk. You have 2 months to prepare.
Sanjoy, just real quick, I'm happy to send this presentation to anybody who wants it. So go ahead and send me an email and I can send this to you. It's all published work, so.
Appreciate it, very much appreciated. Any volunteers for April? I hope you won't mind if I call on you by email. Danny, thank you so much for this very interesting presentation. I learned personally a lot from it, and grateful for the time you took to put it together.
Great, thank you, and I appreciate the questions.
So that's it for this month's webinar. Thank you all for connecting, and have a wonderful month.